So, yeah, if
We can't see the site, sir.
I've started the recording and sharing my screen, and I'll take you to the simulated annealing parameter. Right? Okay. So I hope you can see my screen. Right?
Yes, sir, we can see your screen.
Okay. So in the simulated annealing, essentially so okay, this is the algorithm, right? And you have like local variables as current, a node, next a node, and t a temperature controlling the probability of downward steps, right? So this is something that is fixed, right? And that you give before running, or it is something that is not updated, right? The schedule once given is fixed, right?
Yes.
See, because in this step, okay, just give me a minute. Let me, yeah. In this step, if you see, we just take the temperature as whatever is the schedule, right?
Yes, sir.
So this becomes hyperparameter, and it is not updated anywhere. Whatever is the value, we take it and we just use it. We don't change it, or we don't move it, or we don't play around with that. The only thing we play around is with this delta E, and we check that if it is zero, then we do something. Otherwise, we don't. Otherwise, we don't do anything like that. Else we update the current, and the next only with the probability e to the power delta E by 2. So this is essentially what we do. Right?
But sir,
Yes. Yes.
in genetic algorithm, will crossover rate be think of as a parameter or hyperparameter? Because crossover rate also is not something which changes and is decided by beforehand. But in the lecture, it is
Mhm.
stated that the crossover rate is a parameter.
Random exploration can be found by local search. So is it so? Okay, so let me see.
I think it was in the cons of genetic algorithm. The lecturer said that the one of the cons is that there are too many
So essentially, here I think parameters is a node to hyperparameter, not the actual parameter. I would say. I think so.
Yeah, the
Because
reason I'm asking, yes, sir,
Mhm.
continue.
Yeah, I think this is a node to hyperparameter only. I don't think it's actual parameter here, because by tunable it means you have to tune it by hand. I think so. And, and anyways, crossover rate is fixed, like it's not randomized or anything. Once we pick a value, we stick to it, and that is repeated again and again.
So the reason I'm asking is that there is a question in our assignment. One of the option is like the genetic algorithm has many parameters, but simulated annealing has no parameters.
Hmm. Let me just mhm. Just give me a minute. Yeah. Uh, yeah, I have started sharing my screen again. I hope it should be visible
No,
now.
sir, it's not visible now.
Hello?
Okay, it's now visible.
Yeah. Okay. So, hmm, it's taking so much time. Week four, week four, assignment four. So is the time? No, it is not over yet. Na? So let others attempt. Okay. Anyways, what is your question?
I'm saying in question number four, there's an option that
Mhm.
simulated annealing has no parameter, while genetic algorithm has many parameters.
Mm-hmm.
The thing is, will like as you said, like temperature is not a parameter; it's a hyper parameter.
I think you can consider the parameters here are like, so you understood, right? What essentially where this is going.
Um,
like multiple parameters, and so it says, right, multiple parameters such as crossover rate, whereas in
so
simulated annealing you do have to set a temperature schedule, right?
yes, so yeah, okay, so it is considered a parameter.
Ha, ha,
That's
ha,
what
ha.
that is what I am asking.
In this language you will consider it as parameter, but in terms of machine learning I would say that it is more of a hyper parameter, because it is
And another thing, sir.
something that you
Um,
decide beforehand before you run the algorithm.
yes, sir. In question number one, the variables are not defined. I think it's a wrong question. In question number option number four, as A and I are not defined. So I think there's a problem.
So, minimizing modest, but S, they are giving the definition of S, right? S is a
No,
set.
but
S is the
yes.
set I such that AI is less than AI plus 1. So AI and AI plus 1 are the elements at index I and I plus 1.
Okay, so AI and AI plus one are element of array at index I and I plus one.
Uh-huh.
And what is that I over and then there's this
So
bar.
essentially, okay. So essentially, what it is saying that consider all those indexes. Consider all those indexes where your current index element is less than the next index element, and it is asking you that whether minimizing this set, minimizing the cardinality of this set, does it lead to the desired goal state or not?
Can you repeat again, sir?
Okay, just let me see if I can open one more comment. Open. Okay. Hey. So what it is asking is that what is it? So, or I
Yeah.
think it is just, so it is this set, right? So what will be the set S here? It will be, see, at index one, AI is less than AI plus one because AI is one and AI plus one is two, right? So one will be in this set, similarly two will be in this set, three will be in this set, and four will be in this set. So what is the cardinality of the set? That is four. So do you think minimizing this cardinality would result to a desired goal state or not? Whatever the question, right?
Okay, sir, I understood the question.
Anyways,
Thank you,
I will
sir.
not give you solution because you have to try this one out. But okay, okay, cool. So, are there any doubts in the assignments of the previous week? Let's start with that because last time some people have had some doubts, and you asked me, so that's why I'm asking. Like, does anyone has any doubt, or do you want me to solve some questions or anything that you might have doubt about? Is there a doubt? Yeah. Okay. So you can unmute yourself and directly speak whatever be your doubt. Like, you can tell me the question number, or you can tell me whatever problem did you face. So the most interesting question I think was this one. How many
Hello.
of you were able to answer 10th?
Hello.
Question number 10.
Sir, I scored, sir, right now.
Hmm?
I did the I answered the questions, the tenth
Hmm.
one.
Yes. So
Sir, can we discuss the previous week's questions? I joined in a bit late.
Yeah, so these are the previous week's question,
No,
right?
no, I'm talking about week one. I had some doubts from week one.
Week one.
Yeah.
Okay. I have not covered topics of week one. Anyways, uh,
Will you be covering them later on, or
because these are more or less theoretical. So, what are your doubts? Like, if you go through the slides, I think you should be able to answer them.
okay? I was just referring to the lectures posted online.
Yeah, if you cover the lectures, I think you should be able to answer them. But if you have any specific question now, I think I can check it online and I can answer. So
Okay, okay. I'll just pull those questions out and then get back to you.
okay, so okay, any problems from week two? Because we have also not done solutions for week two. So what did we discuss? And I don't remember. I think we did discuss.
Sir, we discussed the selected question which I asked you to.
Okay, okay.
Sir, sir, can we discuss the week three question, sir?
Can we?
Discuss the week three question, sir.
Oh, sure, sure.
All the
Yeah, yeah.
questions from week
Yeah,
three.
yeah. I asked before only that if you have anything, please unmute and speak here. Okay. Which one?
Sir,
Which one would you like?
sir, all the questions are from one.
Hmm?
All the questions are 10 questions from 1 to 10.
All the questions. Okay. Wow. Okay. Uh, just give me a minute there. I'll just put my laptop. So, how many of you were able to answer the first one?
Uh,
So, what is the first one? First question says, since consider the undirected graph below, the cost for each edge is written adjacent to S adjacent to edge. So, what was the what problem did you face? Like, whoever has asked, what problem did you face? Because we did solve a question like this A star in while in the last class. Anyways, I think we can go over it once again. So okay. So first, let me do the easy ones first. Okay. So the question number second: which of the following functions will result in identical behavior to greedy best first search? So here the function is since the heuristic function for a greedy best first search, it is a function of the heuristic function only. So we can take f of n as 100 times h of n and f of n is hn to the power 2, and these are the only two correct answers. Why why not 1 over h of n? Because in that case the heuristic of goal state would become infinity, because h of n is 0, and you will never come out of the list. Like you will never terminate with a goal state, right? So it will never be 1 over hn, and gn into hn is not an optimal goal cost, because it should be constantly proportional. Like it should be some function of hn, and gn varies for every n, so it cannot be the right one. So that's why we only keep 100 times hn and hn to the power 2, right? Is this question clear? Who- So whoever asked, please at least reply that.
Yes,
Did you understand or did you not? Like,
yes, sir, yes, sir, yes, sir.
okay. Uh, because I cannot go back and forth between the meeting tab and this tab. So I would just request you to whoever is asking the question, please at least reply whenever I'm prompting. Okay, cool. Okay,
Okay, sir.
so which of the following? So for this given graph, right? Uh, which of the following statement is correct? So is the heuristic admissible? So for admissibility, what was the criteria? What was the criteria for a heuristic to be admissible? Can anyone of you tell?
Sir, the optimal cost. must be greater than the heuristic cost of all nodes.
Hmm, exactly, right? So if we if you check for all the nodes, you will find that the optimal cost is indeed the heuristic is indeed less than or equal to the optimal cost, right? You can check for any one of them or you can check for all of them. But for a heuristic to be admissible, it is for all nodes. The heuristic of that node should be less than or equal to optimal node. So I will just show you for, like, let's say A, right? So what is the optimal cost of going from A to the goal state? From state A to the goal state, what is the optimal cost?
10.
It is
Nine.
it is 4 plus 1 5, 5 plus 1 6, 6 plus 3 9, right? 4 from A to D, then D to E1, E to F1, or F to G, or you can directly go from, oh no, yeah, 4, like A D F G, A D E F G, A D E F, all these A D E and G, all this gives you the optimal cost of 9,
9.
and your heuristic is saying it. So for A, it is satisfied. Similarly, you can check for B, C, D, F, and F, E, F, and G, and all. So you'll find that yes, it is less than or equal to, right? So your cost is less than or equal to the optimal cost. So it is admissible. But in terms of consistency, where do you think does this note fails? It is saying that it is not consistent. Now, what was the point of consistency? Can anyone tell?
The difference between the heuristic cost must be must hello the difference between the heuristic cost must be less than the true cost between the nodes, each pair of nodes.
Yeah. So essentially, the formal way to say that is the heuristic cost of a parent should be less than or equal to the heuristic the cost which is required to generate the child from that parent plus the heuristic of the children, right? That is how we show that. Okay, let me pull up the slide in case you want the exact formulation. I can pull it up. Oh, not sheets. Sorry, slides. Like metal. Okay. So here we saw that for a heuristic to be uh, consistent. Yeah, for a heuristic to be consistent, it should satisfy this condition, that for every node n, for every successor n dash that is generated that is generated due to a legal action, the the h of n should be less than or equal to the cost of n comma a comma n dash plus h of n dash, right? So if you see here, if you see in this diagram, can you spot a parent child relationship where that condition is failing?
F and G D
Hmm?
F and D.
F and D. Yes. Yeah. In D, the heuristic is 5, right? Um, why D? So E, it is 4. But see, h of f is 2, right? And the cost of generating the it is 2, and h of d is 5, and 5 is not less than or equal to 2 plus 2. So yes, for d it is failing, and hence it is not consistent. So is this question clear? Okay. Anyways,
Sir,
moving to
please
the
kindly once again, sir, that concept.
okay. So for consistency, your condition is that for every node n, for every successor n dash that is generated due to a legal action, your the heuristic value of your parent should be less than or equal to the cost of generating, essentially the cost of generating n dash from n using that action, plus the heuristic value of the child. So it is in some sense a triangular inequality, right? So here h of if you check the heuristic value of d, right? Heuristic value of d is 5, right? H of d is 5. But if you see that in terms of that the cost to generate f from d is 2. Okay, let me write it down. I think it will be much clearer then. Okay, see what we have the heuristic value of d. This is equal to 5, right? And we have the cost of generating f using the action from d, that is 2, right? And the heuristic of f, that is 2. Now what our consistency says, that h of d, which is 5, this should be less than or equal to cost of f comma a comma d, which is where a is the action that generates f from d, plus the heuristic value of f, right? Is this clear? This is what consistency says. Okay, so your h of d, which is 5, is it less than or equal to this thing? What is this? This is 2, right? And what is this? This is 2. So 5 is not less than or equal to 2. Hence this condition is violated, so it is not consistent. Did you understand now?
Yes, sir.
Okay, cool. Now moving on to the next one. So h of n equals to 0 is always a consistent heuristic function. What do you think? Is this correct?
Yes, sir.
Okay. The second one, Manhattan distance is an admissible heuristic for moving a rook from any square on a chessboard to another square in the smallest number of moves. Do you think this statement is correct, given that all s costs are positive? Okay, so let us think about this for a moment. What is an admissible heuristic? Can anyone of you tell what is an admissible heuristic?
So admissible heuristic is applied when the all the nodes, the heuristic cost of all the nodes is less than the true cost of reaching the goal.
Yeah. So in simple words, a heuristic which never overestimates, right? An admissible heuristic is one which never overestimates. Now think about the heuristic that you have taken, right? So your heuristic is that I want to move a rook. So rook essentially either moves in either horizontally or I would say either in x direction or in y direction. Okay, I think it's better if I draw. So if you are familiar with a chessboard, with the pieces of the chessboard, so a rook, it essentially can move either in this direction or in this direction. That means it can only move straight. It can do no diagonal moves. So let's say in a chessboard, if here is your rook and you want to go here, right? Your heuristic will say that you need to take at least two moves. Your heuristic says the heuristic of going from A to B is 2. But do you think is it correct? Think about it for a minute. Do you think is this heuristic underestimating or is it overestimating?
It's severely overestimating
Yes. And why is it overestimating? See,
because the number of turns required. Okay.
yeah. So you got the idea, because you can go from A to B in just one move, right? But your heuristic is saying that the Manhattan distance is 2, so you will need two moves, and it is overestimating. So it is not an admissible heuristic. Okay, is this point clear?
Yes, sir. Clear.
Okay. Now, depth first search can never terminate faster than A star with an admissible heuristic. this can be wrong, because we saw that if there are infinitely many goals, if there are infinitely many states with the cost as same as the goal state, then A star might never terminate. If you remember the condition for completeness of A star.
So even that is not necessary. A star search with bad heuristic will give you the wrong solution. Will
Yeah.
give you the solution very late.
Hmm.
While if you get very lucky with deep search, you will be able to find the solution in the first iteration.
I'm sorry, repeat. Can you please
I'm
repeat?
saying that if you get lucky with the deep search, you can get the solution in first iteration itself.
Hmm, hmm.
While if the heuristic is terrible in A star search, will might never reach the goal.
Okay. So, okay. Yeah, I'll take your argument. That's correct. And this was the last statement was already covered in the lecture, that a straight line distance is indeed an admissible heuristic for the problem of moving from one city to another. If you remember this example that we discussed of going from, I think, Arad to Bucharest, which is the one which we have been doing since class first. So you will understand that here the straight line distance is always an underestimating heuristic and hence admissible. Okay, so I think that is fine. Right. Now, in this one, uh, which of the following are correct? An inadmissible heuristic might be consistent. And okay, so we will simply just rule out which of them is false. An inconsistent heuristic might be admissible. This I did discuss an exhaustive proof about this, and we clearly proved that if and only if a heuristic is consistent, it will be admissible. So clearly, this statement is wrong, right? If the heuristic is consistent, A star using tree search is optimal. That is true. If the heuristic is consistent, A star using graph search is optimal. That is also true. Because if you remember for this tree search example, like we did discuss an example in this lecture here, where we show that if a heuristic is not consistent, you might end up with a solution which is not optimal. I hope you remember this example. Or do you want me to repeat this example? You can tell. I can do it. Eva, are you trying to say something?
So actually, just the previous example. Could you please solve question number 5?
Yeah, that we will solve. First, I'm discussing the easier ones, and then we will go to the ones which will take some time, right? Okay. Anyways, so I think this. Yeah,
I
yeah.
joined late, so the first question was also missed. So please
Oh, yeah, yeah.
take
Okay,
time in the end. Then
okay,
please.
okay. Sure, sure.
Thank
We'll do that. We'll do that. Okay, cool. Anyways, uh, and in question number 8, in question number 8, so the first statement is correct. We had discussed this last in the last class itself, that max of h1 h2 is an admissible heuristic if h1 and h2 is an admissible heuristic, right? Am I audible?
Oh yes, sir, you are audible.
Okay. And max of h1 comma h2 will dominate both h1 and h2. Min of h1 comma h2, that is also an admissible heuristic because h1 and h2 are admissible, and minimum will even underestimate, so that is an admissible heuristic. However, min of h1 comma h2 will not dominate h1 and h2, so that statement is not correct, right? Now, which of the following algorithms are guaranteed to be optimal? This also we discussed in the last class itself, that A star with zero heuristic will be optimal, and uniform cost search are guaranteed to be optimal. Depth first search is not even complete, and even A star with admissible heuristic might not be optimal, because we saw that if there are lots of states with the same state with the same value as the goal state, then the algorithm might not terminate and hence might not be optimal, right? And for the 10th one, so here you want to sort an array of n distinct integers using a star search. The start state is a random permutation of integers. The expansion function applied on a given state yields all permutation that can be achieved by swapping one pair with all h cost as 1. And there is one goal state, which is obviously the sorted array, right? Now let SP be the number of elements of the array that are not in the position. They are supposed to be in the sorted array. Now, which of the following are admissible heuristics for this problem? So straight away, zero is always admissible heuristic, right? Because it always underestimates. So it can be it is a valid solution, right? SP by 2 and SP by 3 both are valid heuristics, because if SP elements are not in their place, then you need to do SP by 2 swaps, and even SP by 3 is also an underestimating value for that. Now, why SP cannot be, why SP itself cannot be a admissible heuristic, and this can be clearly understood by a very simple example. Let's say you are in a state where all the elements except just two elements are not in their correct position, right? So your entire array is sorted, and there are just two elements, let's say 5 8 comma 5, and the rest of array looks like 1 2 3 and 4, right? Now what does your expansion function will say? Your expansion function will give you 1 2 3 4 5 and 8 with the h cost of 1, right? And this will be your goal state because your array is sorted, right? So what is the cost of going from this state to goal state? It is 1. But what will s of p give you? S of p will give you 2, because 5 and 8 are not in their correct position, right? So your heuristic is giving value 2, but your optimal value is 1, and it is not less than or equal to 1. Hence it is not admissible. Do you understand?
Yes, sir, understandable, sir.
Okay, nice.
Sir,
Huh?
in many other courses, the answers to the previous assignment are given in PDF format, so that if anybody wants to like check it, they can refer to that. Uh,
Yeah,
and
that can also be done, but still, if someone wants to, like, my job is only to help you guys with the doubts only. So,
yes, sir, but yeah, that will be more efficient, no?
huh.
Also, I wanted to have some. I have some confusion in the lecture as well. It's like the week for lectures.
Week 4 lectures.
Yes, sir.
Confusion. Okay. Uh, okay. So just give me, I think. So, which one of the two questions do you want me to solve? Question number 1 or question number 5? I can.
Sir, both. Sir, both.
Sir, both 1 and 5, sir.
There is not so much time. Okay, let me see if we can search this on Google. Is this available on Google?
So no, sir, no questions are available on Google, but I can share my solutions.
Let's
So no explanation are given. The answers are simply, you know.
Okay. So are you giving your quizzes by searching on Google and answering, or you are solving the questions and then?
Sir, no, those answers are not correct, sir. The person who made those answers does not know how to solve those questions as well. So if you copy the maximum score you will get is 4 or 5.
Okay, right. Here
You will never be able to break through more than that.
it is saying GS, BA, GCAG, whereas here it is S.
That's why I said, sir. The answers, the person who made those cheat sheet do not know how to solve this question.
Okay, no worries. So, okay. So both of the examples are of tree search only, right? So if I do one, I think you will be able to solve the other one. I see that. See, both of the one are tree search A star. Here it is also tree search A star, and here also it is tree search A star, right?
So this is on directed one, the other one is directed one.
Yes, sir, that's true. The first question is bidirectional, and
Uh-huh.
the question, fifth question is unidirectional. But I don't think that would make much of a difference.
Yeah, but if it is unidirectional, then tree search A star, I think it becomes more or less like a graph search. But yeah,
Without
if there
duplicate
are
detection, sir.
back edges kind of thing, then it can become like a graph. But yeah, I think we can just solve one of them, and you can try the other one. If you still face an error, we will take it up in the next class, right? Just in the interest of time, we will solve only one of them. Okay. Uh, where it is copying. No. Cool. Okay. So this is what we have, right? Hmm. So you you have to solve this using the tree search. Okay, so let us go over the tree search thing once so that you remember, right? So in the tree search, what you do, like, you take the fringe, you have a fringe in which you store the successor, and while fringe is non-empty, you take the node, you remove first, you get to the state, and if that is a goal state, you return the solution. Otherwise, you insert all the successors, right? So here there is no notion of keeping an explode set, and you just do like you just see that if you just consider all the state as new states that you have never seen before, right? Cool. So you are doing A star search on this undirected graph. Assume the heuristic for a node is the least number of edges required to reach from that node. For example, h of A is 2. Okay, it is the least number of edges, right? So we will just quickly put the edges. So what will be h of s? Can anyone tell what will be the h of s?
So H of S is given as
Yeah, it's
exception to
given as
the.
it.
ठीक है. Okay, if h of s is given as 0, we'll consider it 0. नहीं क्या? Okay, h of s is defined as 0, and since we can reach g by the path abg. Okay, cool. h of s is given as 0, h of a is 2. ठीक है. So h of a is 2, right? Similarly, h of b is 1, h of c is 1, and h of g is also 1. Sorry,
Zero.
h of g, 0. Sorry, yeah, obviously because it is a goal state. And okay, right. So you start from s, right? You start from s. Now from s, you can go to a, or you can go to b, right? So okay, so this is 2, and this is 6. Now h of b is 1 and h of a is 2, right? So which fn is smaller? F of n is smaller, right? Because f of a is 4
Hmm.
and f of b is 7.
7.
Yeah.
So we will expand a.
Hmm.
There is some noise. If you are not participating, please mute yourself. Like, if you don't have anything to say, please keep yourself muted. Okay. Okay, so this part is clear, right? H of A is 4, f of A is 4, f of B is 7. So we will pick A to expand, right? Now from A, where you can go? From A, you can go to B, or you can go back to S, right? So from A to S, what is the cost? It is 2, right? And from A to B, it is 3, right? And h of s is 0 and h of b is 1, right? So what is the heuristic of s? So okay, we'll also maintain what states we have explored so far. So we started from s, then we picked a, right? So h of s is 0 and f of s is, sorry, and f of s is 4, and uh,
This is 5, 6.
how 6?
F of
Yes,
B is 6.
f of b is
F of
6.
B, yeah, f of B is 6. That is correct. F of B is 6. So now in the frontier you have S with the cost of 4, B with the cost of 6, and another B with the cost of 7. So you will pick S with the cost of 4, right? So what will be your visited state space look like? It will again go back to S, right? It will again go back to S. So it will be S, A, and S again, right? Now from S again, where you can go to A, or you
Or
can
B.
go to B, right? A with the cost of 2, B with the cost of 6.
But HA has also equal to 1. HA is equal to 1. The heuristic of A is
H
1.
of equal to 2.
No, the path is 2, but H of A is equal to 2, I think.
No, but that is already explored. We are going like in this direction. We are going
No,
down.
so even if you go, it is SA, then S, then A. But A, are you not taking into account H of A here, heuristic? Is it the
Where?
final? Because it's not the goal. So HA will be considered here.
Where?
So the last A that you have reached, SASA.
No, so we are now picking which state to expand. We have not done any expansion in the current. See, so far we have traveled this path. Like we went from S to A, and then we have gone from A to S.
Hmm.
And now from again S, where you can go
Yes,
to A or you can go to B,
that's fine.
right? And H of A is 2, and H of B is
It is
1.
8. So H of A is equal to 8 now.
No, no, H
So
of no, no, H
F
of A
of
is
A. F
2.
of A is equal to
Yeah,
8.
F of A is 2 plus 2 plus 2, 6, plus the heuristic, which is
Yes,
8.
yes, that's correct.
So f of A is 8,
Hmm.
and f of B is, so can anyone tell what is f of B? 2 plus 2, 4, 4 plus 6, 10, 10 plus 1,
11.
11.
right?
Hmm.
So in the frontier, you have f of B with 11, f of B with 11, f of A with 8,
Hmm.
and you have 6 and you have 7. So you will expand this one, right? F of B, f of B is 6, and this is the least cost node. So you will expand this one. So SA, SB. So are we correct so far? What does the solution says?
Sir, is it
Sir,
SASB
you
or
are correct.
directly SAB?
No,
You are correct, sir.
SASB.
So why it is like this? I
Because
mean,
it
you
it
have
is
to put the path. So I mean, S
no, no,
A
no, no,
and
no,
B.
no.
Then
No. See. Just let's go over the question once more.
yeah, here is my doubt.
Okay.
The
Just
question does not.
कहाँ गया question? Go to code.
Sir, the
Okay.
question is not about the path, sir. The question is about the
The
exploration, the order of
exploration. Yeah,
exploration.
exactly. The
The
even
question is not asking for
uh,
the path.
the question is about exploration, right? That you have correctly pointed out. Just see the question once. What does the question ask? The question asks the order of exploration. Find the order of exploration of states. And that we are noting here. This is our order of exploration of states. So we have so far explored SA, SB, and then we will continue further from B. And then you can take away from here. Like I think it is fairly easy to do like this.
Yeah, that's fine. Yeah, here was my doubt. So
Hmm.
I didn't see that exploration part.
Oh,
I was
okay.
always thinking it's
Okay.
sort of
So I think this one is also then like
this one
here
also.
what we
Please
have to do.
explain. Maybe that will be the problem here.
Huh?
I think here also, if it is exploration, then
Okay, let us read. In the directed graph given below with edge weights as cost and heuristic values of node written in red, tree search A star is performed. Consider the two subcases, right? Uh, so what in the first case, 5 node expansions are performed. So just like we did here, you have to construct the tree in a similar fashion and then see like how you're expanding the nodes.
sir, in the first case, if you are expanding it, then it is 0, then 3, then 7, then 6, then 4. So 4 is the goal node. Now if it is correct, then it
See,
will
I
be
have
only
not
4
solved
nodes.
it, so I don't know. But if you are saying it like that,
Um, I can help, sir, if you mind.
huh?
I can help her.
Yeah, like
I
if
have,
you have solved, you can also share your solution. Like you can share your solution either in the WhatsApp group that you created in the last session, I think you did
Sir,
create
actually,
some sort
it's. I mean, I'm not being able to connect to the WhatsApp group. It's not. Although I clicked on it, it's not
like
actually
I don't know.
not
I'm not
doing.
Okay.
part of it. I'm just saying that I saw that someone posted a link. So, okay. Anyways, so what? So from consider two subcases. The ties are resolved by choosing the node of larger index by smaller index. So this I think is should not be a that big of a problem. Like 0 and 1 goal node 4, right? And how the heuristics are also mentioned, right? So from 0 you can either go to 1 or 3, right? You can either go to 2 or 3 and your goal state is 4, right? So so you can go to 2 with the cost of 5 and you can go to 3 with the cost of 3. So you will go to the 3 with the cost of 3 because that is cheapest, right? 2 plus 1 3. Now from 3 you can only go to 7, and what is the cost that you will pay? You will pay 2 plus 1 3 plus 1 4. So then you will pick 7 because you have 2 with the cost of 5 and 7 with the cost of 4, right? So from 7 you can only go to 4, and that you for that you take 2 plus 1 3 plus 3 6, and 6 plus 0. So there is 4 with the cost of 6 and there is 2 with the cost of 5. So you
Sir,
will
you
pick
can
2 with
go
the,
from 7 to 6 also.
sorry, yeah, you can go to 7 to 6 also. So uh, okay, 2 plus 1 3 plus 1 4 plus 1 5, 6 with the cost of 5, 4 with the cost of 2 plus 3 5 plus 1 6, 4 with the cost of 6, 6 with the cost of 5, and 2 with the cost of 5. So here you are picking the larger index, right? Here you are picking the larger index, so you will pick 6 with the cost of 5,
Yeah.
right? So 2 1 3 1 4 and 1 5, and then you have 4 with the cost of 5, right? Because you are doing 3 stars. So
Sir,
you
4 is
will,
the goal.
huh?
4 is the goal.
4 is the goal. So you have expanded 5
4
states.
nodes. Sir, 4 nodes, na? How you have expanded 5 nodes?
See, you expanded 3 7 6 and 2,
And 0, 0. No.
and 0. Yeah, and 0. So
Yeah, so it's
you
4.
can consider, yeah.
Sir, how it is 5 nodes? That's the first option that I do not understand.
Acha.
Sir, the reason it's 5 nodes is because uh,
अच्छा
zero.
you explode बोल रहे हैं या अच्छा node
Expansion. It's
expansion का problem.
expansion.
अच्छा it should be from 0 you go to 3 or 2, then from 3
Sir, there's a tiebreaker. There's a tiebreaker. You have to solve a tiebreaker in the question. This node 6 has the same heuristic as the node 6 has the same f function as the node 2. So, and depending on the way you break this tie, the answer will be different. The first case is when you break the tie with the greater
That's
number.
fine. Yes. So that's
So
6.
the total number of expansion which is done in the first case is equal to 5, depending on the tie you break, depending on how the tie is broken.
Hmm. No, but what I don't understand is how this is equal to 5.
So
Can you
because
explain that?
0, 2, 0, node 0, node
Hmm.
3, node 7,
7,
node
not
6,
6.
Yes,
and
that's
node
all.
2.
Now, why node 2 is to be expanded? When you reach 6, at that point it is equal to
1 3
5.
1 4
5.
1
So
5.
2 is to
Heuristic
be
of 4 is
expanded.
5.
But
Heuristic of
expansion
4
and
is 5, and
exploration.
heuristic of uh, heuristic of 2 is also 5. So you will pick heuristic of, you will pick 4.
No,
That is
so
correct.
4 is not there, it's 5.
That I agree. That I agree. So let's so just think of it as how many 5 node, how many nodes have you explored? I think.
Sir, is it exploration?
I think the question there, this is a mistake, sir. This is certainly a mistake.
Yeah, it should be 5 nodes explored, like, because
Yeah, it should be exploration, yeah, not expansion. There's a mistake in the question, sir.
Hmm.
She's right.
Yeah, yeah. I understood your doubt. I understood your doubt. Either it is 4 node expansions or
Yes.
it is 5 node exploration. Yeah, I totally agree with you. There must be some formulation error. Anyways, these are drafted by human only, so there is always.
So will we get, sir, bonus marks on this? Because in Joy of Python, when we tell the instructor that some questions are wrong, we would get bonus marks for them.
You can talk to the instructor. Like, I have no idea how that pipeline works. you can connect with the instructor and you can decide.
Sir, question number 2, if you can discuss regarding
That we
HN.
already discussed.
Oh,
Question number two I
sorry,
already
sir. Okay, if
discussed.
someone can share with me, then it would be good.
Can you join the group?
But
Maybe.
I'm unable. I mean, I'm not being able to join, even though I click on the link that was
Okay.
given.
Anyways, let's not discuss it here. Let's just be okay. So I think we can move to the problems for week 4 then.
Sir, in previous question,
Which one?
first question,
Mm-hmm.
sir, can you explain the last step? That selecting among the frontiers.
The
How
last
you select the node B?
selecting among frontiers.
Yes, sir. वो जो last in the last step you have selected B, S, A, S,
हाँ हाँ.
and how is it done?
See, because what you have in your frontier, you have B with the cost of 6, A with the cost of 8, B with the cost of 11, and B with the cost of 7. So 6,
Oh,
8, 11, 7. 6 is the least cost, so I pick
you
B.
are considering B two times.
Huh?
The you are considering B two times, na? The
Yeah,
last one.
it's a graph search. It is a tree search, not a graph search.
Okay, sir.
It is a tree search.
Okay, okay.
In graph search, you will not consider it is a tree search. Like if you see in a tree search, you just add. Whereas in graph search, you check that if this node is explored or not.
Okay, sir.
Right?
Thank you, sir.
Okay.
Sir,
And then,
exploration, in case different paths are explored, then also the order of exploration will be like this. It's not the shortest. I mean, it's not the shortest path or
this
minimum
is
optimal path.
we are talking about tree search version,
Mm-hmm.
and this is not a path.
No,
See,
I understand. Yes. So
path
that
anyway, you will backtrack. Like if you explore B, then you will go to G, and then okay, let's just complete it.
no,
So
no, I
from
understood, sir. This way that you
yeah.
explained, that is understood. But
So from B, you will go to G or C, and then I think as per the solution, you will just end with G because it is 2 plus 3, 2, what is this? 2 plus 3, 5 plus 2, 7, and that is, uh, and I think you will just end here by like,
SASBG, SASBG. That's
huh.
all.
Yeah, and the path that you will take, then you will backtrack. So how did you come from? How did you land on G? You came from
So
B. How
if
did
the
you
path
came
is
to
to
B?
be found out, then will it be SABG?
Yeah, it will be SAVG.
Okay.
This is the state of exploration.
Okay.
This is how we have visited or how we have explored the graph.
Hmm.
Okay, so I think we can end this one now, and we can go to the doubts of lecture 4, like of week 4, or yeah.
Yes. Yes.
Sir, so in there's a slide in the lecture where the professor discusses about finding the number of expected restarts
Yeah,
and the
this
number of
like see,
expected resets.
in this week I have not kept that many slides. Like now I am feeling bad. Like
Okay.
earlier I used to keep all the slides. This time I don't have that many slides because you said that you are not that interested in slides.
Yeah, I said like I want you to share the slides with me. I said,
Uh,
yeah,
uh, okay, anyway, so what is your doubt? Because I don't know the exact slide, so that might be a bit of a
yeah.
problem.
So the one of the question which is discussed by the Professor Mausam was that what will be the expected number of restarts and
Mhm.
steps in the local search problem given there is a probability P that it will find a solution. Um,
Do I have it here?
in the it was at the very end.
Yeah, I think it
The
was this one.
local search with the random restart.
Was
Yeah,
it this one?
yeah, exactly this one. This one, sir.
No.
Exactly this.
Okay.
The
What
yeah, this one, sir.
what is the problem?
But yeah, the expected number of restarts, he gives us the answer that the answer will be 1 by p, but he does not give us the method with which he reached that answer.
So expected number of restarts is, he said, is 1 by p,
Yes, sir.
and he does not give. Okay, let me see. Just give me a minute. I'll just load that one.
He
If I
stated that this
can,
is a problem to be solved by the
let's do
students.
a Google search. Like, what's the harm? Expected. So did you find it on Google? Anything similar to that? Like,
Nothing, sir. Nothing. Not on Google.
what was this problem? Expected number of restarts.
In climbing hill problem, climbing hill with restarts. Climbing hill with restart. Expected number of restarts.
Climbing with random restarts. Let's see. So um, yeah, so I think there is something here. Let's see. If you can find something relevant, we can spend some time on it. But so what does the professor comments here? He says that it is 1 by p.
Yes, sir. He says that the solution is pretty trivial, and thus he will not be going to be providing one. But I was unable to compute the solution.
Okay, so let me see whether it is discussed in the book also. So did you check the book?
No, sir. I did not check the book.
Okay, let us check the book then. Right? We have the book also, so there is no problem. We are talking about random hill climbing, right? So that is
Yes,
search.
sir. Hill timing with random restarts.
Hill climbing with random restarts. Let's see. Local search and optimization problems. So we directly jump to simulated annealing. Why?
The book is not very as thorough as the professor's teaching, though. That's I find surprising.
Okay. See, you can find the solution here only if you read. So the hill climbing algorithm describes so far are incomplete. They often fail to find a goal when one exists because they can get stuck on local maxima, right? So random restart hill climbing adopts the well-known adage: if at first you don't succeed, try again. It conducts a series of hill climbing searches from randomly generated initial state until a goal is found, right? If each hill climbing search has a probability p of success, then the expected number of restarts is 1 by p. Okay, the book itself just states this. Now, can you think of why it is trivially complete with acha? Okay, so see, you think of it as you think of it that way. Like if it is trivially complete with probability approaching one, because it will eventually generate a goal state. If you read these two statements, you will see what you are looking for, right? If each hill climbing search has a probability p of success, right, and each of these random restarts are independent of each other, right? They are mutually exhaustive events, right?
Yes.
Are you with me so far?
Yes, sir. I am getting you so far.
Okay. So what does our probability says? That summation of all such p's that should be equal to 1, right?
Yes, sir.
And how many
Summation.
times we will add this p? We will add this p as many times as we do restarts.
Okay.
So np is
Yes.
equal to 1, so n will be equal to 1 by p. That is a very straightforward solution
Okay.
actually, right?
Yeah, yeah, yeah.
You read these two statements, right? It is trivially complete with probability approaching 1 because it will eventually generate a goal state. If each hill climbing search has a probability p of success, and these events are mutually exhaustive because you are doing it randomly, so it will jump to a completely new thing which might not be even related to where you have come from, right?
Yes, sir.
Then the expected number of restarts is 1 by p.
Yes, sir. The solution is pretty clear
Okay,
now.
cool. So
Um,
did everyone get this or not?
Yes, sir.
Cool, that's great.
one more thing, sir.
Please ask.
So the in the lectures the professor discussed an algorithm, the random restart algorithm. But after that, he come to a much more universal algorithm where he says that instead of going to a random state after reaching a local maxima slash minima, we
Mhm.
should have some probability of choosing a bad step that takes us to a less value.
That
Uh,
describes simulated annealing, no?
Yeah, the simulated annealing, yes, sir.
Yeah, yeah.
But I still don't understand the intuition behind why we are choosing like random step at the initial level when we already know a good solution in the search space.
No, see, the
Instead of
point
like
is you don't
choosing,
know. You don't actually know, right? See, the why we are doing random restarts because you are getting stuck at a local maximum,
yes, sir.
right? And what the idea of simulated annealing is to improve the quality of local search. So instead of picking the best move, you can pick one randomly. Say the change in objective function is delta. If delta is positive, that means you did find a good state. Then you move to that state. Otherwise, you pick the state that you are getting from this state, even if it's worse, with some probability. Because there is always a chance of escaping from local maxima where you might get stuck. See, the idea is very simple. Like, let's say if you are stuck here, then eventually you will get down this curve because you are taking bad solution until you start climbing the hill again. That is the intuition, that you want to go down before you start going up. So you pick that one, you pick that bad solution with some probability. That is the entire idea, that even if it is worse, you take that, because that will help you to go down from this local minima, from this local maximum. So you will get down, and then start going up. So is this intuition clear?
Yes, sir.
Hello? Yes, is this intuition clear? I just want to get an idea.
Yes, sir.
Okay. Let me see. Can we find something here also? Simulated annealing. Okay. So here it is says that a hill climbing algorithm that never makes downhill move towards state with lower value is guaranteed to be incomplete, because it can get stuck on a local maximum. In contrast, a purely random walk that is moving to a successor chosen uniformly at random from set of successors is complete but extremely inefficient, because you will end up jumping a lot of times before you actually go to a global maximum. So this is something of a middle. This is something of a middle ground between completely hill climbing and completely random walk. So the book clearly says, therefore, it seems reasonable to try to combine hill climbing with a random walk in some way that yields both efficiency and completeness, and that such algorithm is simulated annealing. See, that's why I'm emphasizing since first class that you please start reading the book. There you will clearly find solutions to what, not the entire solutions, but maybe the intuitions or some minor problems that you might be facing.
Sir, it is the third edition of the book or the second edition of the book?
I
It's
think it is the third one. If you
third.
want, can I put it in the chat? Let's see.
No. Sir, actually, I'm going through the second edition, but this 4.1.2 is not available in that. That's what I'm asking.
I don't think I can send it here.
Yes.
Okay, I think I'll add it to the Google Sheets. If you want, I can keep it in the Google Sheets or in the Google Drive. Like,
Yes, sir. Please share the book, sir. We don't have the copy.
okay, let me see. Okay, I'll do this after the lecture, right? I'll do this after the lecture. Okay,
Thank you, sir.
okay, cool. So now, so I think most of you have gone through the lectures, right? I think many of you have gone through the lectures for this week, or no?
Sir, a part of it I have gone through, not all.
Okay. Achha, this one is already taken from the lecture itself. This, although these are old assignments, but yeah, cool. So, okay, then we will just do a simple problem solving thing then. So, which of the following algorithms is asymptotically complete? Random sampling of states, local beam search, random walk, or hill climbing with random restarts?
Last two certainly are.
There is a
Sir,
lot of points.
the presentation is not clear. It's not in high resolution. So can you either zoom in or?
Oh, sure, sure. Yeah, I can always do that. You can just let me know. Okay, is it visible now? It should be.
Yes,
Otherwise,
sir. It's
The
visible now.
best visible is possible.
just visible still.
No, sir, it is. I mean, it's much better.
Visible, sir.
Okay, cool. So these are from the past sessions. Okay, so which of the following algorithm is asymptotically complete? Random sampling of states, random walk, local beam search, or hill climbing with random restarts? So we just now saw that random walk, sorry, what did we, so see, local beam search, other than local beam search, see, random sampling of state is complete, random walk is complete, and hill climbing with random restarts is complete. So I think this is a theoretical question. We'll find the answer once you go through the lectures, right? Genetic algorithms are set to jump from one hill to another. Which of the following is responsible for such behavior?
I think it's crossover, because the in one crossover the solution is state is very far away from the initial solution.
Hmm. Yes, your answer is correct, and we can see it from the slides. Just give me, just let it load. Yes. So in genetic algorithms, when you do this crossover, where you take two fit parents and you take some part of the first one and some part of the other one, so essentially you land in a completely new part of the search space. So yes, this is also something which is directly taken from the lecture. So yes, it is, the answer is crossover, right? Now Mona has a hill climbing problem to solve. She observed that her problem might often get stuck in plateaus. Now, which of the following additions to the procedure would you recommend to her? Okay,
Allow indefinite recycling.
see,
Allow,
allow indefinite side moves. Will it be a good idea?
yes, sir, definitely.
Okay. So so does everyone know what is the definition of plateau?
Plateau Pathar is
Okay. So a plateau is a flat area of the state space landscape. It can be a flat local maximum from which no uphill exists, or a shoulder from which progress is possible, right? A hill climbing search might get lost on a plateau, right? So you have to remember this point, that a hill climbing search might get lost in a plateau. Now, if if you allow infinite sideway moves, I think this part was also discussed in the lecture. If you think clearly, why this might not be correct? I'm not betting my money on this. Like, if you allow indefinite side moves, you will get there. I won't bet my money on this. I might be wrong, but still, can anyone think why it might not be correct?
it will only work with the shoulders, right? It won't work with plateaus without shoulders.
Okay. No, no. So the word that I might give you as a hint is, think of cycle.
Cycles.
Yes.
So cycles will not be possible, sir. I think allow sideway moves up to certain limit 100, and then keep a taboo list of recently visited nets. That will also do.
No, but why indefinite sideway moves might not be correct, right? It might not be correct. I
Then,
won't bet my money on it.
then it
Because,
will keep oscillating, sir.
huh, yes. I think it was also discussed that if you do like
Yes.
this, then you will end up in
Absolutely.
an infinite loop and keep on generating same states. Like going from this to this to this to this, and so on. And then you might come back to the same state again. I think something like
Yes, sir. But if the algorithm runs long enough, if there is a way to get move off the plateau, it will definitely find no. With when we
this,
allow
you cannot
So
indefinite
in that
cycles.
assume,
case, sir, in that case, second option and third option, I
you
think.
can see, you cannot make such assumptions, right? The problem is, you cannot make such assumptions that you will move out of the plateau.
If there is a like, I'm not making assumptions, sir, but if there is a way to get off the plateau, allowing indefinite cycles move will certainly help, because there is a some probability that if there is a shoulder, like if there is a maxima
Mhm.
with which we can go up from the plateau with infinite with enough of step, the algorithm will traverse through all the points in that plateau, and if there is a hill, it will find it.
See, the keyword here is often gets stuck in plateaus, right? If it is off, like if it gets stuck in plateaus often, it means that it is highly probable of being a flat local maxima than a plateau, than a shoulder. Because if it is a shoulder, then she might not get stuck very often. See, again, if you read the book, it clearly says, right? The algorithm halts if it reaches a plateau where the best successor has the same value as the current state. Might it not be a good idea to keep going? Exactly as you are saying, right? To allow a sideway moves in a hope that the plateau is really a shoulder. The answer is usually yes, like I was saying, but we must take care. If we allow a sideway moves when there no uphill moves exist, an infinite loop will occur whenever the algorithm reaches a flat local maximum that is not a shoulder, right? And then it takes the same thing, like it takes exactly the same thing from the book, that you put a limit on the consecutive sideways moves that you allow. Are you getting what I was trying to argue?
Yes, sir, definitely. So yeah, so if there is a plateau, there is a chance that the algorithm will get stuck in that
Flat
plateau.
shoulder. It is a
But
flat
this
local maximum.
yeah, it will stuck in the flat local maxima and
Hmm.
never give us a solution. But and will never terminate, which is like
Hmm.
opposite of what the local
Yes.
cell is supposed to do. It's always supposed to terminate after some time, right?
Yes, exactly. So so that's why we just put a limit, say 100, which they took from the book only, which I just showed you. And the next idea would be to keep a taboo list and then to perform a BFS. So all these three methods were discussed in the lecture also. You can correct me if I am wrong. I think all these parts were discussed, like a taboo
I
list was
don't think
discussed.
the infinite the sideways moves was discussed. I don't remember.
Yeah, the indefinite side moves were discussed, and there I think sir told that if you are in a flat plate, if you are in a flat maxima, you might get stuck in a cycle kind of situation, like an infinite loop kind of situation, which is the same as mentioned in the book, and you will never get it. You will never get out of it. So it's not a good idea to bet your money on that. But what you can do is to put a limit on the number of consecutive sideways moves allowed, right? So if you do that, then you can say, like, you can save yourself. So this raises the percentage of problem instances solved by hill climbing from 14 to 94%. Wow, even I did not read this before. So success comes at a cost, but that is fine.
Sir, it is discussed in the lecture.
Yeah, I think it was discussed in the lecture. Yeah. So and the last option is last option was also discussed in the class, that whenever you are stuck, you just start a BFS till you find a node which is better than your current state, and just keep going from there, right? Okay. The fourth one: which of the following is or are true about local search algorithms? So can anyone of you would like to take a guess on this one? Which of the following is or are true about local search algorithms? First, they are guaranteed to always terminate with a correct solution. They are highly memory efficient. So, okay, what about the first one? Is it true
It's
or false?
obviously
Wrong.
obviously
False,
false.
false.
Yes, false. What about the second one?
Obviously
True.
true.
What about the third one?
I'm not sure of.
Okay. And what about the fourth one?
Yeah, the third and fourth option are the same thing.
No, the third and fourth are not the same thing. The third is
Fourth
like
is true.
the third is that they can only solve a certain variety of optimization functions. So, for example, it can only solve those optimization functions which are convex in nature, or which are like which have only one local maxima, which have two local maxima, which have only one local minima, or it can only solve optimization problems which are which corresponds to the class of minimization or maximization. So things like that. Is it true?
No, the
No,
third
they
is not
don't make
true.
any
The
such
fourth
assumption.
is true.
Fourth is true.
Yeah. So third is correct. Third is false, and fourth is correct. Cool. So they are highly memory inefficient, and they don't make any assumptions on the structure of optimization function. Great. Now the fifth question is that I think that is already discussed, that if your probability of random restart, if your probabilities of success is 0.14, so then you will do 7 restarts, right? Because it came from this formula. Number of restarts that you will need to do is 1 by p. Here p is equal to 0.14, so n is approximately equal to 7, right? Cool. The next one, this was also discussed in the class, like the famous FF planner uses which algorithm? Heuristic search, enforced hill climbing, iterative deepening search, or greedy hill climbing with random restart?
Second one.
Yeah, second one.
Which one?
Second one.
Yeah. So it is enforced hill climbing. So what was enforced hill climbing? Let me see. Do I have the slide for that? So I think enforced hill climbing was the one with the BFS or what? I totally forgot that one.
Yes, sir. Once we get stuck in a local minima, local maxima slash
Yeah.
minima,
Yeah.
we
So
just
this
use PFS.
So enforced hill climbing is the one with the BFS, like perform breadth first search from a local optima to find the next state with a better heuristic function or the better objective function. Sorry, heuristic might not be the right word. Better objective function. Typically, prolonged periods of exhaustive search bridged by relatively quick periods of hill climbing. Yeah. So gradient descent is guaranteed to converge for strictly convex functions, assuming the step lambda is sufficiently small. Now we have this graph of y equals to x square. For what value of lambda will gradient descent converge? Okay. So for what values of lambda will it converge? Can anyone take a guess on this?
Uh, I
0.1,
think
0.5, 1 and 2.5. Okay, so before we go to this, let us first discuss what is gradient descent for those who might not know that. Okay, so let's assume that you have a continuous function. Let me put this in a slideshow mode. Okay, the slides are visible, right? Hmm.
yes, sir.
Okay, so assume we have a continuous function. In this case, that is f of x squared, and we want to minimize over continuous variables, and we only have one variable. So we compute the gradient for all the variable and take a small step downhill in the direction of gradient, right? And uh, and you just keep on repeating this process till you hit the minima, right? So what is the minimum value of f of x square? Like y equals to x square. What is the minimum value of the function that you can get,
Zero.
Zero.
right? So your graph is y equals to x square, and your derivative, right? Your gradient delta of x, that is just 2x, right? That is 2x, right? Your derivative. See, compute all the gradients for I and take a small step downhill in the direction of the gradient, right? So your derivative is 2x because your y is x square, right? So del of f of x with respect to x, that is equal to 2x, right? So in x you will do x minus so xn plus 1 will be xn minus lambda times
Del of
2x 2x n with whatever value you have, right? So if you want to take it like if you want to approach this value to 0, right? So if you start from a point that is okay, so let me draw the curve, then you will get this. So here I am drawing this curve y equals to x square, right? So it looks like this. It's simply a parabola, right? And this is 0 0, which is the minimum value. And I know it's not perfect, but yeah, this is y equals to x square. Now what will happen if you keep this lambda very big, let's say greater than 1, right? So what will happen is once you reach here, you will jump here you will actually exceed, the maxima, because you will subtract too much, right? You will subtract too much. Let's say if you are at 0.8, right, which is very close to 0, and so 0.8, it will be lambda times 0.8 minus lambda times 2 into 0.8, 2 into 0.8. So this will be 0.8 minus 1.6 lambda, right? So you want to keep your lambda not too big, right? It should not be too big, because if you keep big lambdas, you might end up actually overshooting your minima. And from here, you will go back here and you will just keep swinging back and forth, back and forth, back and forth, and you will never converge on the optimum. So it is ideal to keep smaller values in case of gradient descent. Is the idea clear?
Yes, sir.
Okay. So for what values of lambda do you think it will converge?
First and second.
It is
Um,
0.1 and 0.5.
is
Because
there any a hard proof, sir? Because is there any way to prove that it will not converge for 1 or 2.5?
you can clearly see, right? If you see this example, if I put lambda 1 here, right, and I was at 0.8, so what will be my new xn plus 1? Just think about this. What will be your new xn plus 1? It will be 0.8 minus 1.6, right? So it will be minus 0.8. Now from minus from minus 0.8, you will find your next xn plus 1. So what will it be? It will be minus 0.8 minus 1.6 times lambda, which is 1. So you will go to minus 2.4. So now you have actually started going away from your maxima.
Yes, sir. But we are is there any if the problem is a bit more complicated, the derivative of this is pretty easy to calculate. Is there any algorithm that can find us? I think the professor discussed some line
Yeah,
algorithm,
yeah. So
but yeah.
essentially, there is a separate class of algorithms in machine learning that you can use. So line search is one of the examples that professor discussed. Other is like some kind of step size. So you do step. So just like you vary temperature, right? Just like you vary temperature in the simulated annealing, you vary your learning rate. You vary your learning rate. So this type of procedure is known as I think it is step scheduling. You can search the terms online, but these types of things are called step scheduling. Step scheduling. So what happens is, like, when it is your first step, you keep your lambda as 0.1 or 0.2 or even 1.0 when you start, because you might start anywhere, and the first step you naturally want to take is a big step, right? But as your iterations increase, right, you keep on decreasing the step size, let's say by a factor of 0.1, right? So in the first step it was 1, then it was 0.1, then it was 0.01, then it was 0.001, and so on till it does not fall below a certain value. For example, 10 to the power minus 5, something like that. Or you can simply half it. So from 1 you can go to 0.5, from 0.5 to 0.25, 0.125, and so on and so forth. So these types of algorithms exist. It is some are step scheduling. Then there is another class which does some sort of exponentiation. There is exponential scheduling or something like that you will find. So all these types of algorithms you will find in either PyTorch or TensorFlow. If you are familiar with these frameworks that exist in the world of machine learning, so if you check out their pages, there you will find various types of learning rate scheduling algorithms. If you want, maybe I can pull up one of them. If you want to, I can just show you learning rate schedules. PyTorch. Let's see. I'm trying my luck here. I don't know. Yeah, it's a learning rate scheduler. So there are different types of schedulers, like yeah. Okay. Are there here? No, these are the types of learning. How to adjust learning rate, right? So these are like, if you find a plateau, you reduce your learning rate on plateau. So there are different types of things. there is exponential LR, there are multi-step LR. So normally you don't fix, so in ideally you don't fix the learning rate. It varies with the iterations that you do, right? Am I clear?
Yes, sir.
Okay, cool. Fine. So today we might end up in time also. Wow. So for question number 8 and 9, we are doing simulated annealing. Okay. In simulated annealing, generally there is a chat. My bad, something on my. Okay. Anyway. Huh. So in simulated annealing, generally the temperature is reduced from a positive value to a low value in the successive iterations. Assume the following three-step temperature schedule: 20, 10, and 0. Assume that we have three states: S1, S2, and S3, such that V of this is this, V of S2 is this, V of S3 is this. Successors of a state are chosen uniformly randomly. Okay. Assume S3 is the start state. After the first iteration of simulated annealing, what is the probability that the current state would be S2? Okay. So let's go over simulated annealing before we come here. So the basic algorithm pattern is this. You have a function simulated annealing which returns the solution state. Your input is the problem that you have, and schedule, which is a mapping from time to temperature, that at what step you want what temperature, right? Then you pick up whatever is your current node, and for as many steps as you want, you do the following. First, you take the temperature that from your schedule. So in our case, schedule is 20, 10, and 0, right? So T is the schedule. If T equals to 0, then you return whatever you have. Then what you pick as a successor next is a randomly selected successor of current. Now delta E is the value of next minus value of current. If delta is greater than 0, then your current becomes next. So if delta is greater than 0, that means you have found a better state from your current state, right? And then you take that current state. Otherwise, you take this bad state with the probability e to the power delta E by t. Okay, so I'll just copy this slide here. Let's see how it goes. Uh, cool. Okay. Okay. Nice. Hmm. It is visible, right? I hope the pad is visible. Okay.
Yes, sir.
And this is our scheduling state, and this is our problem question. This is our question description. I'll copy here. 10 0 is our scheduling state, and assume S3 is the start state. So what do we want after the first iteration of simulated annealing? What is the probability that current state would be S2? This is what we have to calculate. Okay, that sounds like a good question. Let's try. Uh, see, so it is asking that after the first iteration of simulated annealing, what is the probability that the current state would be S2, right? Your start state is S3. Okay, so your start state is S3, right? And from S3 you can only go to S2. Okay, cool. So and we know that V of S3 is 10 and V of S2 is 0. V of S3 is 10 and V of S2 is 0. Okay, cool. Okay, so the current is this, current state is S3, huh? And your and what we have, so we have T at so we are taking time step as 1, right? Because this is our first time step. So T, which is the temperature for the current step of T, is 20. If you see it from here, T of T is 20. Okay. Now what we do? Now think what we do. So is our T zero? Is our T zero? We check, is our temperature zero because of this statement? Is our, because of this statement, is our T zero? No. So that means we continue. Then we pick up next successor, which is a randomly selected successor, right? And what is the successor of S3? It is S2, right? So that means our next is S2. Now what is our delta E? So delta E is the value of next, which is value of S2. And what is our value of current? It is value of S3. So this is 0 minus 10, which is minus 10, right? And this is less than 0. So we will not do this, but we will do this. So it will be e to the power minus 10 divided by 20, which is e to the power of minus 2. And you can check on calculator or anything like, let's see, do I have a, I will have a calculator, obviously. Does it have a e? Do you see? Okay, so e to the power, how do you put to the power? Okay, anyways, we are doing,
Sir, it's 0.135335. 0.135.
okay, so you calculated that, cool.
Yeah,
So
0.135.
e to the power
E to the power minus 2 is
delta
0.
E by T. So delta E by T is 20, and this is 10. So e to the power minus, oh, sorry, not minus 2, e to the power minus 1 by 2. What I'm doing, sorry. So it is 1 over square root of E, not e to the power minus 2, e to the power minus 1 over 2.
So that is 0.606.
Exactly. And that is what we are getting here, 0.606, and it is 3 digits, so rounding of 0.607. Cool.
Wait a second, sir. Wait a second. The what's assume answer?
Yeah, it is 0.607, na? You got
Okay, sir. Yeah.
0.606 and we are getting 0.607. So it is fine. It is 0.001 anyways.
Yeah, sir. Sir, that's the thing. Like it's rounding off to the greater.
No, so even if you input here 0.605, it will accept because
Oh,
these things are not hard coded. So what professors normally do, they will put like this in the in while they are submitting the answers, they will put a range. So they will start from, let's say, 0.6 to 0.61. If your value is in between this range, they will approve. Like that is what is ideally expected. Like when we
yeah.
had this orientation session, it was told to us that if you are setting the answers to the question here, so you are supposed to give a range, not the exact value, because like 0.606, 0.6076, so between 0.6 to 0.1, if you enter, I think it should be fine. Okay.
Yes,
Now
sir.
let's do the second one. What is the probability that when the algorithms end, we are at the, oh wow, this is a very weird question. What is the probability that when the algorithm ends, we are at the state with the highest value? Okay, so we started with S3 and we we are at S2 now. So we are at S2 now, right? We are at S2
We are
now
assured the probability of 1 upon root E.
with 0.6, right? S2
Yeah.
with the probability 0.6, right? So this is our current. Now S2 is our current. Okay. So from S2, where we can go? From S2 we can go to S1 or S3, and both of them have a higher value than this, right? So from S2, okay. So I think this can be done via that. How can you figure this one out? Successes are chosen uniformly
Sir,
from
I
S2,
think the probability of choosing S1 will be 50% and the probability of choosing
and the
S3 will be
0.5,
50%.
0.5. Exactly, that's what.
Yes, and then we multiply it by the probability of switching to S1.
Acha, so you are saying that okay, we are at S2 and now we go
We are
to,
at, okay, so there is a 0.6% probability that we are at S2, and there is a 50% probability that we will go to S1. Now,
hmm,
we will choose S1, not go to S1. And then we will multiply this probability by the probability that will go to S1 given that we have chosen this. And then, so this will be the total probability of going to S1 in two steps. And you do the same thing for the third step, and we haven't even considered the fact that we might not even move to S2 in the first step. It will be a very complicated question.
Yeah, because they are saying what is the probability that when the algorithm ends. So when does the algorithm end? So
After three steps,
it's after the three steps.
because the delta is temperature
The
is zero
temperature
after the
becomes
third
zero.
step.
Okay, so let us do that. Okay, so let's say, okay, let us do that. So from S2, so we picked S2 with a probability 0.6. Let us keep it here. Okay, so from S2 you can either go to S1 or S3, right? So each of these are picked with probability 0.5, 0.5, right? So with S3, what can if you come back to S3, you can only go to S2, right? And that will be again, so that will be picked this, but this time S2 will not be picked with the probability e to the power minus 1 over 2. This time the probability will change. And
This the probability will be one because it's greater than. And if we
no, no, no,
find a
no.
greater value,
No, no. If we go from S2, you can go to S3 or S1, right? And
yeah.
from S3, you can only go to S2.
Mhm.
Okay. But if you go from S3 to S2, you are saying that your delta is less than zero. That means your probability will change. So you are picking it with the probability of e to the power delta e by t. You are picking it with the probability of e to the power delta e by t. And your delta is minus 10 and your e is 10. Your t is 10. So this time you will pick it with probability of e to the power minus 1.
Yes,
Okay.
sir. Yes, sir.
And then from S2, you can again go to, uh, then from S2, you can again go to S3 or S1. And again, so this time it's fine. So you will anyways end up at a better state, right? However, from S1 you can go to S2 only, which is also a bad state, right? So from S1 you go to S2, which is a bad state, and from S3 also you go to S2. What kind of problem is this? Huh. Okay. So from S1 you go go to S2, and here you find that your delta E. What is the delta E this time? The delta E this time is 5, right? Because V of is everyone able to follow this? See, V of S1 is what is V of S1? Just see. What is V of
So give
S1?
S1 is 5, sir.
V of S1 is 5, right?
Yes,
And
sir.
what is V of S2? V of
Is
S2 is
zero,
2,
zero.
right? So if we go from S1 to S2, our next is S2 and our previous is S1. So it will be e to the power minus 5 over the temperature. And what is the temperature here? Here the temperature is 10 because we are at the second stage, right? Okay. So this one was 0 point. So this one was 0 point. So e to the power minus 1 over 2, right? So this is e to the power minus 1 over 2. And again from S2 you will go to either S1 or S3. And how you came from S3? You came from S2 via S3. And this is where you will stop. This is where you will stop because your temperature now will become 0. So how does our state exploration looks like? So from S3 you go to S2 with the probability of e to the
Point
power
6.
1 over square root of e, right? Which
Yes.
is 0.606, 0.606, right? From S2, you can go to S3 or S1, each with the probability of 0.5, 0.5, right? Now
Yes,
from
sir.
S3, you can pick S2, and from S1 also you can pick S2. Here, the probability is e to the power minus 1, and here the probability is e to the power minus 1 over 2, because here delta E, here what is delta? Here delta E is minus 10 and T is 10. Here delta E is minus 5 and T is 5 and T is 10. T is still 10, right? So yeah, and then you are at S2, S2. So and then you see Acha, no, but okay. Sorry. Let me think for a minute. I am confused. This is a very difficult problem. So okay, if t becomes zero, then you return the current. This is first step. This is second step. And if your t
Yes,
becomes
we
zero,
won't go more further than this.
so what I think is this will not happen. I think this will not happen. Can you guess why? See, because in the first step, right? In the first step, what was the first step that we go from S3 to S2? And this we did with a probability of 0.606, right? Now, here the temperature was 20, right? Then from S2, you can go to S1 or S3. At this step, the temperature is already 10, right?
Yes.
Because if you check the algorithm, what does the algorithm says? That you take the t of the schedule, which is the second step, and it is 10. Now at the third step, right, at the third step, which you will take, here t becomes 0, right, and you will return the current solution. So you will return S1 or S3. So essentially you will take this, the probability of this entire path. So it is S3 to S2 to S1, and it is S3 to S2 to S3. And I think if you add both of these, you might get the value. I'm not very sure. I'll have to check back with the solution manual once, but I think it should give you the value. But
Wait
I'm
a
not.
second, sir. So you're saying that if there are three temperature schedules given, we the only the first two are the one which is counted?
Mhm.
Okay, sir.
See, as soon as the temperature becomes 0, right? So what is your temperature of the schedule? Your temperature of the current schedule is 0, right? So whatever you have, you return, right? So whatever you have, you return. So if you follow S3, S2, S1, you end up with what you end up with. S3, S2, S1, you end up with S1. If you follow S3, S2, S3, you will end up with S3
Sir,
because
we
here
haven't
t is
considered the
0.
probability of 1 minus 1 upon root e of going remaining at S3.
1 over
1 minus 1 upon 1 upon root e, which the probability of remaining at S3.
probability of, no,
Remaining at S3 in the first step one.
no. Why do we remain at S3? See,
Yeah, we remain in S3 because there's just only small chance. Like the sum of probability will always have to add up to 1, sir.
no,
And
no.
if the
See,
probability of
no,
going to S2, yes, sir.
no. Don't think of it this way. It is not probability. Do what the
It
algo
is
says.
it
What
is
does the
probability.
algo says? If delta is greater than 0, then you switch the next with the current. Otherwise, if delta is less than 0, then your current will become the next, which is your successor, which in our case is S2, with this probability, with e to the power delta E by t, right?
So we will have to consider the other branch, no? That the probability where the S3 will remain at S3.
But why from S3 you will remain at S3? See,
Because the
once,
S2 is going bad, right? The value of S2 is less than S3.
no, from S2 you can go to S1 and S3, and you have to go to S1 or S3. See, next of S2 is S1 and S3, and you can pick each one of them uniformly.
So you're saying that if there is one node, if a high value node is connected to a low value node, we always have to go to that low value node.
No. So what I am saying is that, see, this is what we discussed previously, na, that let it be a low value node, right? Let it be a low value node, but you still go there with some probability.
And
But you
so
go there.
what's the other probability, right? The other probability is only remaining at S3. Like sum of probability will always have to add up to 1, sir.
Hmm. Achha,
That
that.
is a universal law.
Oh, okay. That what you are saying. Okay. Simulated annealing. In metallurgy, the process used to explain simulated annealing, such a point of view from hill climbing to gradient descent. The innerest loop, if the move improves the situation, it is always accepted. Otherwise, the algorithm accepts this move with a probability less than 1. The probability increases exponentially with the badness of the move. The amount delta E by which the evaluation is worsened. Sorry. The probability also decreases as the temperature goes down. Bad moves are likely to be allowed at the start when T is high, and they become more unlikely as T decreases. If the schedule lowers T slowly enough, the algorithm will find a global optimum with probability approaching 1. This is what it is saying. This is what the book says.
One more question, sir.
Mm-hmm.
Yes, sir. You said like the algorithm will terminate just before the temperature reaches zero, right? Just before.
No, no, just not just before.
On the
On
step
the
where
step.
temperature reaches zero, but
On the
we
step.
can,
See, I am not saying it is written in the slide. Like if T approaches
yes,
T becomes zero, then you just return current. And by returning you mean you terminate. You
yes,
terminate
sir.
that.
But in the current assignment, assignment number 4, there is a question where only three schedules of temperatures are given. And we are asked to find what will be the solution at step 3. But according to algorithm, the step 3 will never happen
Why it will not happen?
because the algorithm ends at step 2 anyway. Because the step 3, the temperature is zero.
Yes. Okay.
So what does the questionnaire mean by saying find the value at step 3?
So essentially at step three you have you so what will be the value? At step three, what will be your value? So the value that you will be return will be value of S1 or value of S3, depending on which successor you choose to explore. Right? So
No,
at third
sir.
step,
I'm
from
not talking
third
about the
step,
S. I'm talking about the step.
so what is the question? Let me okay. But if I solve that then
No,
uh,
I'm asking you to solve it. I'm asking you to like, what does the question mean?
okay,
Uh,
so okay, let me just go to that course. Just switch there.
so it's question number 7.
Okay. This was a very weird question. I did not think it through. Sorry for this. Uh,
It's a very similar question, sir, to the one. Question number 7, sir.
okay.
Yeah.
Hmm. So assume the run terminates after three steps. No, yeah, so it terminated after three steps. It terminates at step third only. It does not terminate at see at second step. We have S1 and S3 as the node that we want to explore. But when you go for the third step, so this is third step has happened. But at third step, we see that the temperature is zero. So
So
we
the
just terminate it here.
so the
Terminate
answer of step 2 and step 3 will be same.
the answer at step 2 and step 3 will be same because you have that successor, right? Because that is in your current node. or
Okay,
or
sir.
let me think. See, at your step 2, if you are at step 2, right? If you are here, right? So this was the outcome of step 1, so this is your next, this is your current, right?
Yes, sir.
Step 1, this is your current, right? So what you do at step 2, you just update the next, right? Because if delta is greater than 0, then you switch your next with the current, right? And from S2 you can only go to S1 or S3. So at the outcome of step 2 you have S1 or S3. Huh. And when you go for the third step, you see that your schedule is your temperature for this step is 0, so you return. You simply return. You simply
Okay,
return with the
sir.
current.
So the statement that the solution at step 2 and step 3 will be same is correct?
For this, like, yeah, I think it will be correct.
Okay, sir.
Given that you are at an optimal successor, that is the underlying thing. Because if you are not, then you will update your if your delta is less than 0. Acha, okay. ठीक है. If your T becomes 0, then you simply return the current. Yeah, so there is nothing to do there. Uh,
Okay, sir. Understood, sir.
yeah. If your T becomes 0, then you just return whatever you have. Yeah.
Yeah. So two more things.
Mhm.
First, like if even if the temperature value is not being used because the node which is selected is already like guaranteed to move up. right? But
let me,
even if the temperature is not being used, we will consider that we have, yeah, matlab that will be like moved out of the array, right? We will not use it again in the next step.
what you will not use again in the next step?
Like, say, for example, in the step one, we do not use the temperature given
In step
because
two, we do not use the temperature. Yes,
in
yes.
any step, for example, in a hypothetical question,
Mm-hmm.
we do not use the temperature because the node selected is
Mm-hmm.
already has a high value. So there is no
Mm-hmm.
need for user temperature. We are guaranteed to move to that node,
Yeah,
right?
that might happen, but that
That
might
might,
not always be true. That's why we have this safety
yeah,
condition.
yeah. But in that case, do we repeat? Do we reuse this temperature until it is used, or we will say, yeah, we already
You,
used it
you
and
will
move to
use
the next temperature?
you see, the idea is that at first you can take bad steps. That's why you keep the temperature high, because you can take bad steps. But as you go deeper, you don't want to spend a lot of time going on bad states, so you reduce the temperature gradually. But if at any step your temperature is not considered, that does not mean that you will not count the schedule. You will not consider the schedule value at that particular step. Because see, it goes from T1 to infinity. Your temperature is checked every time, irrespective of it, whether you have used or you will use it or not. Because you don't know beforehand whether you might use it or not. It is only when you compute delta E you decide whether to take this node or to take some bad node with some probability.
Okay, sir. Also, sir, where can we find the previous year's assignments?
Where can we find? Oh, actually, only we have access to them.
Sir, because in the last session you said like we are supposed to solve the assignments, but you didn't give us any way to do it because you didn't have those questions.
So that's why I spent this like in this session. I thought that let's solve some questions. Okay.
Sir, actually, question number one, with respect to the last option that's given, what is the meaning of S?
So that was discussed in the beginning. Okay, let me just take you there. I think
Sir,
I.
this will be
Okay.
included, sir.
Cool, cool. Yeah, yeah. So let's say your array looks like this, right? 1, 2, 4, 5. In the question, what it says is the S is a set of all those indexes such that the value at that particular index is less than the value at the next index. This is what the set S is. So for the current for for the current array, the set S will contain the index 1, will contain the index 1 because a1 is less than a2, will contain index 2 because a2 is a of 2, which is 2, is less than a3. It will also contain index 3, it will also contain index 4, assuming that here it is infinity and here it is -1. Like you can think of something like that as the corner cases.
Yeah.
So your cardinality of that set is, so mod s essentially means the number of elements in that set, and it is 4.
Yes.
Okay, is it clear?
Yes, 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 sir.
So if you minimize this objective function, does it leads to the desired goal state? That is what it is asking in this question. Okay, so let me just quickly go over. Anyways, I think the question that we were solving, it is asking that what is the probability that you will end up with a highest goal state. I think that is what it was asking. Let me just see. What was
Yes,
the
sir.
word?
Yes, sir. The highest value gold state.
So
Well,
then,
where will you hide?
then you can do the Bayesian rule, right? That P of this divided by total probability. And I think you will get this answer 0.552.
Yeah, again, sir, if you share us this question, we can solve it and check.
Sure, I'll anyways it is in the it will come on YouTube. Like you can just see, right? It will be there on YouTube, so you can check. You can check.
Sir, what's the 10th question can you like for the YouTube? The
So
10th question.
so the 10th
Okay, sir.
question is What are the differences between simulated annealing and genetic algorithm?
Answers.
This I think this you have to solve in the current one, right? So I will not show you that.
That's not fair, sir. That's a previous year's question.
I will not show you the answer. Okay, cool. Chalo. I'll end this session now and thank you for attending. Bye bye.
Sir, hello, sir.
Yes.
Sir,
If there are
yeah,
any doubts or anything, you can
sir, can you
definitely.
provide this problem solving session? Hello,
Can you?
provide this problem solving session video within this week.
Sorry, I'm not able to hear you
Sir,
clearly.
sir, can you provide this session video link in this same week?
Yes, yes. This will go up on YouTube. This will definitely go on YouTube.
No, sir. In the previous cases, the video is uploaded after the week.
Yeah, he's asking that there's a lot of delay between
Uh,
the lecture and the when you
video.
upload the video. So he wanted you to
No,
like
no, actually, that
hurry
delay
up.
was in
Like
the NPTEL side. So what I do is after just recording this lecture, I upload it on YouTube immediately.
Okay.
And
Okay.
I think by tomorrow morning you will be able to access it.
Okay.
You won't have that much delay now because you have the access to the sheets, right? Like you
Yes,
have
sir.
access to these sheets or not? Like
yes, sir, we have access to problem solving sheets now.
hmm,
Yes, sir.
this one. So like I'll put it by tonight itself. I won't take much longer than that. So you can come back and visit this anytime you want. Okay,
Thank you, sir.
Okay, sir.
cool.
Excuse me, sir.
Yes, yes, yes.
For the previous problem-solving sessions, we were not able to see the slides which I have shared,
Yeah,
sir.
I'm terribly sorry for that. Actually, there was some issue with my recording, with my screen recorder tool. So this time I have tried a different approach. I hope it works for the best.
Okay, is there
I
any way to
accidentally
get those
recorded
slides,
some
sir?
other screen and whatever. But I think while I was presenting in the live session, it was visible. Like, can anyone confirm for those who are
Yes, sir.
here?
Live session, like of course it was visible. Otherwise,
Yes,
we
sir.
would
It
have
is
told
visible,
you.
sir.
I'm really sorry for that. Yes,
I missed those sessions, sir. Is there any way we'll get those slides, sir, again?
the slides of all the sessions are available online.
Really?
No, sir, the one you
Where,
have
sir?
shared.
The one,
For the previous weeks, like 2 and 3, the one which you have shared during the sessions, problem-solving sessions, those slides, sir.
yeah, those slides are available online. Like if you go to the Google Sheet and if you check that folder, that will lead you to the slides only. Do you want me to share and show you? Like,
If
just,
it's available there, I'll check it, sir. Thank you.
just give me a minute. So here, if you check this folder, so there is this presentation folder link, right? If you visit this folder, you will find the exact slides. However, this week there were lesser slides, so you will not find much of it because it was more on the solution part. But I think I'll upload this notes part because we did solve some problem here that might be of help to you.
Sir, actually, in the previous week,
Thank
the
you, sir.
presentation folder link was not available. YouTube link was there and backup video link was there. But this is this new, this presentation folder link?
Yeah, actually, someone merged this column. Now I split it up and I've
Okay.
put it separately, so you will find everything here now.
Okay, okay, sir.
Okay,
Okay, sir.
fine. So, are there any other doubts, comments, anything? So, I'm stopping the recording so you can talk freely.